Welcome. Let's do some ionic compound naming. We're going to change between chemical formulas and names. So we're working with ionic compounds, which means we're going to have a cation and an anion. And that cation is often going to be a metal. So it's worth taking a look at the periodic table, making sure that we know our metals versus non-metals down pat. If your periodic table doesn't already have this, I like to add the metalloid staircase. Some people call them semi-metals. They have properties in between being a metal and non-metal. All right, so here's our metalloid staircase. Everything to the left is going to be more metallic in character. They're going to be your metals. All right, and so that's most of the periodic table. And those are going to be your potential cation choices. And everything to the right of the staircase is going to be your nonmetals. Those will be your potential anion choices. Let's go over some vocabulary. So in the previous video, we were talking about naming molecular compounds, and we were naming like a molecule. So the single unit for molecular compounds is called a molecule, if you have one single molecule. We're going to need a different phrase now that we're talking about ionic compounds, something like sodium chloride. A single unit for ionic compounds, we don't call it a molecule, we call it a formula unit. That's because it's not a molecule. In a molecule, you have shared electrons, whereas in an ionic compound, you have ions. All right, so let's really illustrate this. So again, we have sodium chloride, okay, just table salt, or if you're a geologist, halite, whatever, rock salt. So in this formula, you actually have a sodium plus cation and a chloride anion. And in forming an ionic compound, you need to have the cation and anion already existing in order for them to have the attraction between the positive and negative. If I had neutral sodium and neutral chlorine, they would just be separate until they collide and an electron from the sodium gets transferred to the chlorine. All right, they need that collision in order for the electron to be transferred. All right, so if it helps, you can kind of think of that as the process of forming a cation and an anion. And now we have that ionic bond in between them. So, but back to the vocabulary. This is mostly a vocabulary-oriented video. So you may be thinking, how come I just can't call this a molecule? I have like one molecule of sodium chloride right here. Well, that's because you can't really make molecules for ionic compounds. They don't work that way. Like if I had water, dirty water. Right. So if I had some water, you know, right now it's liquid water, and then if I were to heat it up, all the waters would blast apart, into the gas phase, and but they would still have that H2O chemical formula going on, 2 H's, 1 O. Right? With ionic compounds, unless you're at like really insanely hot temperatures, even then it wouldn't work. But with ionic compounds, on the most part, they stay solids until you get to very high temperatures, and at that point, you would maybe have a liquid, an ionic liquid. But you need to maintain a high temperature typically for that. And if you were to blast it so hot that you were to like blast apart things, then you wouldn't even have molecules at that point still. So just fundamentally, basically, you can't have a molecule for ionic compounds. But let's just pretend we're at low temperatures. So we have solid sodium chloride. Here's one. Here's another sodium chloride. And, you know, let's say you had sodium chloride dissolved in water, but then you're evaporating the water, and you're going to leave behind sodium chloride crystals, table salt. Shake on your French fries, right? You know, you keep growing that crystal, and you get something like this. Okay? You can see my individual formula units in that perfect 1-to-1 ratio between sodium, the blue ones, and chlorine, chloride, the green ones. But if you had one single crystal of sodium chloride for your table salt shaking on your French fries, you wouldn't call this entire thing a molecule. If I were to take like a single crystal, even like a really dinky one on my French fries, it'd be like sodium 1 million. It's probably a much bigger number than that. And then chlorine 1 million. This seems a little bit ridiculous to write. Even though that is the unit. If you have one crystal, that is the atomic count of each of the ions. So, what am I getting at here? The idea is that when it comes to ionic compounds, rather than expressing an actual count of atoms, what we do instead for ionic compounds is we express things in the lowest whole number ratio possible. So here's the summary. Chemical formulas for molecules, like water, are usually expressed as molecular formulas. That's a fancy way of saying we're just counting the number for each element in the molecule. But for ionic compounds, like sodium chloride, we express their chemical formulas as they're called empirical formulas. Empirical formula is just a fancy way of saying the most simplified whole number ratio. Because, like we said earlier, we're not going to write sodium 1 million, chloride 1 million. That seems ridiculous to write. Okay, we just find the most simple unit, the simple whole number ratio. We can see in the crystal lattice for sodium chloride, sodium and chlorine are in a 1-to-1 ratio, so we just stick with that most simple ratio. All right, so with that vocabulary out of the way, I think we can get to learning how to name stuff. Here is our template for naming binary, meaning 2 elements, binary ionic compounds. You're going to have your cation name and just a name straight from the periodic table, and that's usually going to be a metal. Put a space, and then your anion name, that's usually going to be your nonmetal. But for that nonmetal, you have to end it in -ide. That's going to be your default ending for the anion name. All right, so we don't say sodium chlorine, we say sodium chloride. All right, this should remind you of naming molecules where -ide was that default ending. That -ide is usually going to be your ending for your more electronegative element, if you've studied electronegativity. If you haven't, you can see a different video, or you may not have to worry about it too much here, but yeah. So 4 things, 1, 2, 3, 4, cation, space, anion, -ide. All right, let's do it. All right, so we're gonna do like we did in the molecule video. We're gonna have formula to name examples, then we're gonna have name to formula examples. People usually find that a little bit more challenging. And then we're gonna end with what's wrong with this examples, and then fixing that. All right, so let's get a periodic table handy. Na, sodium, Cl, chlorine. So we say sodium, chlor, but we don't say chlorine. We're going to use that default ending of -ide. Basically, whenever you have a -ide ending, that means you have the anion version of that element existing. All right. If you say -ide, that means you have a Cl minus. You don't have a neutral chlorine. It's the minus version. So, like chloride ions, you go get a blood test or something. They're measuring chloride in your body. They're measuring for that ion in your body. All right, sodium, and then O is oxygen. So we're gonna, instead of oxygen, we're gonna say oxide. All right, magnesium chloride. Someone's mowing the lawn. Hopefully that's not picking up too much. All right. Now, notice so far, if you haven't noticed already, there's no prefixes. Like in molecules, you have the prefixes, and that's because you need the prefixes. Just to kind of refresh your memory. We can't just say carbon oxide for both of these, okay? This is carbon monoxide. This is carbon dioxide, two very different molecules. So we need prefixes here. But I'm not going to explain it just yet. I'll explain it in the next slide, but we don't need prefixes. Usually in a Chem 101 or even Chem 111 curriculum, they teach to not have prefixes with ionic compounds. All right, so I'll comment on that in a bit. All right, magnesium oxide. All right, aluminum chloride. Or some of you might be saying aluminium chloride. Aluminum oxide. So if you're like, hey, this doesn't seem too bad, you just get the cation name and the anion name and that's it. Yeah, it's that good. Until we throw in polyatomics and type 2 metals. That'll be the next video. All right, no one's laughing. All right, so next, let's do name the formula examples. All right, so potassium chloride. So this is where, like I said, some people find this harder. We're gonna have to go to the periodic table and we're gonna have to use some knowledge of charges, all right? So, when we form a compound, an ionic compound, the tendency is to either lose enough valence electrons to get to a previous noble gas, that's for the metals, or for nonmetals to gain enough valence electrons to be like a noble gas. Okay, so the long story short, everything in this first column, the alkali metals, will have a tendency to become a 1+ cation. As written on the periodic table, it's not a 1+ yet. Okay, that's if it were to lose 1 electron. But that is a very common thing to happen. 2+ with this column. All right, transition metals, I can talk about in a different video, but I'm sticking with Chem 101 here. So the boron column, this would be a 3+. And then the carbon column can be 4+, or it can be 4-. Okay. It's usually 4+, but there's a handful of times, like carbides, you can have a 4-. Carbon, carbide means the minus version. And then going this way, we're going to have 3-, 2-, 1-, 0. Okay, so 1+, 2+, 3+, 4+, or 4-. 3-, 2-, 1-, 0. That's one of that's a common favorite thing to do for chemistry students when they first get their exam. They'll get the periodic table and they'll just go slap out those charges for your monoatomic ions. Mono meaning one atom. Monoatomic, one atom ions. So what does this mean for potassium chloride? Potassium, if it were to be an ionic compound, it wouldn't be neutral K, it'd be the 1+ K. So, that. And then for chlorine, it'd be a 1-. My suggestion is do so much practice that these charges become second nature. So in an ionic compound, you don't write the individual charges on the ions. I didn't come up with the rules, that's just the way it is. You consolidate and someone would just have to know what those charges are. All right, so we have to think. If potassium's a 1+, chlorine's a 1-, chloride's a 1-, how many do we need of each to make this a neutral compound? All right, so because that's what nature's going to do. Nature, you have when you find ionic compounds in nature, they're going to be, or you make them, they're going to be neutral. The pluses and minuses equal each other on each side. So the answer is 1. We only need one of each, so we would write KCl. Okay, how about potassium oxide? Potassium is K plus again. Oxide means we're talking about oxygen, and we are in the 2 minus column. So we're going to have O2 minus. Okay. Now we can't just write that, KO, knockout. That'd be nice, except this doesn't exist in nature. If you find potassium oxide, you make it in the lab, you will find that the potassiums are in a 2-to-1 ratio with the oxygen. All right? And that's because when these are in the presence of each other, oxygen needs 2 potassiums to neutralize its 2 minus charge. Each potassium only carries a 1 plus charge. You cannot make it magically a 2 plus. Potassium's 1 plus, that is just what it does. It only has 1 valence electron it can lose. So it's stuck being a 1 plus. So here's a handy method called the crossover method. I'll move down just in a moment. Here we go, crossover method. Some teachers do not like to teach this because there's a potential for math hygiene to become a problem. I'll show you what I mean in a moment. But like crossover method, I do like it. I like teaching it. You write out the ions, and if you have a 1, we'll just be okay with writing it for a moment. Okay, 1 plus, we have O2 minus. So what you do, write the element straight down, but to get to the, what is it called? The least common multiple. It's not necessarily the least common multiple, but common multiple. To get to a common multiple of charge between the 2 elements, you just swap these charge numbers and you turn them into your subscripts for the opposite element. So we would get K2O here. All right. So let's check our charges. If we have 2 potassiums, we have a total of 2 plus in the world. Oops. And if we have 1 O2 minus, we have a total of 2 minus in the world. We need these to add up to 0. Okay? That's how ionic compounds work. The pluses and minuses mix with each other until everything is neutral. Okay? There's no law saying we need only 1 of each atom. Okay? Most ionic compounds, you're not going to find it that way. Okay? Sometimes you get lucky with potassium chloride, it's 1-to-1. Table salt sodium chloride is 1-to-1. But a lot of them, you're going to have like 2 of something, 3 of something, you know, whatever. All right, so crossover method. I love it. Use it. It's great. Where some teachers get scared of crossover method is, what if you had something like a lead 4 plus cation and then an oxygen 2 minus? You would go PB. You would go O. That 2 you put there. And that 4 you go there. And it looks like the answer is PB2O4. This is electrically neutral, so that's like a step in the right direction. But remember, when it comes to ionic compounds, we have to express things in the lowest ratio possible. So I don't think that's too hard, though. I think we can just look at this chemical formula and be like, well, they have some common factors we can factor out. We can factor out a 2 on each side, and then we would get PbO2. And indeed, that would now be a legitimate, good chemical formula for an ionic compound. Okay, so the long story short with crossover is do it, but remember to have a math hygiene step to remove any common factors. With that being said, let's go ahead and finish this page. Ca2 plus for calcium. There it is in a 2 plus column. Cl minus. Okay, we can do crossover on this one too. Getting a little messy. 2 plus 1 minus Ca1 Cl2, and we don't write 1, so we just go CaCl2. Calcium oxide, Ca2 plus, same oxide as earlier, O2 minus. Even though they have 2s, we only need 1 of each. So CaO. Okay. Whenever I do calcium oxide, it always reminds me of like cacao beans, chocolate, whatever. Anywho, all right, gallium chloride. Gallium is in the same group as boron and aluminum, so it's going to be a 3 plus. How do I write a G? There we go. So we need 3 chlorines on the gallium per gallium. Gallium oxide. Gallium is going to be a 3 plus again. Oxygen is going to be a 2 minus. Looks like I need separate paper here. Okay, the 3-to-2 ratio is very common in chemistry. So we're going to need a common multiple of 6 here. Okay, we can do a seesaw method. Okay, seesaw method is you just kind of fix whatever's lacking. So right now we have more positive than negative, so we just get another oxygen. Now we have 4 minus versus 3 plus. Then we say, oh, now we need more plus. So we added another gallium. Now we have 6 plus and we have 4 minus, so we add 1 more. And then we just count how many of each we have. 1, 2, 1, 2, 3. So gallium 2, oxygen, we have 3 of them. So that'd be gallium oxide. Or if you want to do the crossover, that works too. Ga2O3. Okay. There used to be these old toys that existed. This is like the Jigsaw Puzzle method. Puzzle toys. Yeah, I don't own one myself, but like using gallium and oxygen, you would find something like, let's see, the toy would be like, it'd have like 3 in-pointing teeth. And then you'd get like an oxygen with 2 outward pointing teeth. Right, and then you see that like they don't line up the same, so then you'd have to get like another oxygen or oxide tooth. But that doesn't line up either, so you're like, oh, I need to get another gallium tooth. Let's see if I did that right. There we go. 1, yeah. And then you'd get another oxide with those 2 teeth, and then finally they're all lined up and happy. So there's those Jigsaw Puzzle Toys out there. I haven't seen them in a while though, so hey, make them if you want to make a buck. All right, cool. And then lastly, we have gallium nitride. Okay. Nitrogen, nitride, that's going to be an N3 minus. Where's my periodic table at? There it is, N3, oops, N3 minus. We only need 1 of each, so you get GAN. Okay. You see this material being mentioned a lot nowadays for like premium cell phone chargers and whatnot. All right, we are almost done. I always like to end with some incorrect examples. All right, so what's wrong? So Na2Cl2, what's wrong with this one is, well, let's look at the charges, Na plus, Cl minus. So this is a step in the right direction. You have the same number of each here to maintain a net zero charge. So at least it has net zero charge. But it's not simplified. Okay, so we can just divide a 2 out from each side and we get NaCl, and that would be correct. All right, how about this one? Na plus, Cl minus. This one does not have net zero charge. It is not net zero. If we have 2 chlorides, we have a total of 2 minus, whereas here we only have a total of 1 plus. So if you were to add these together, you'd still have 1 minus, which is not 0, so we would just change that to a 1. All right, and then lastly, what about the name dipotassium monoxide for this chemical formula, K2O? So I like the thinking here. Di meaning you have 2, mono meaning you have 1 of the oxygen. But in most chemistry curriculums, this is taught to be redundant. Okay, that is considered to be redundant information. Okay, because the 2-to-1 ratio between potassium and oxygen is already known. It's already known due to charges. Okay? So we don't use prefixes traditionally in ionic compound naming because the charges already tell us what the ratio should be. Like potassium is a 1 plus, oxide's a 2 minus, so we can see to neutralize the oxide, we already need 2 of the potassiums. Okay, so in other words, just by knowing the charges, you know the ratios automatically. All right, so my closing thought is this. I went to IUPAC, okay, and good for IUPAC. They admit that naming is not everyone's cup of tea. But I went to IUPAC's naming guide. It's called like the Red Book for. They have like a blue book for organic chemistry naming. They have a red book for inorganic chemistry naming. And I saw some examples where they were like okay, totally okay with using here it is. Like look at Ca3P2. Tricalcium diphosphide or calcium phosphide. It looks like in their most updated version, it's like they're okay with prefixes. I'm not like ready to like tell others about this quite yet because I feel like I don't know, like what the chemistry curriculum we have taught for so long, ionic compounds don't use prefixes. But here they're saying, oh yeah, you can go either way. So maybe someday we'll start playing that tune a little bit louder that either way is okay. But to be safe, most Chem 101 curricula, my experience, and as well as software packages for homework, do not accept prefixes for ionic compound names for the reasons I stated earlier. So maybe that'll change in our lifetimes, but I think that's kind of where things stand for now. All right, future videos will include type 2 metal cations where more than one possible charge is possible. Iron's my favorite example for that. Iron can be 2 plus or 3 plus. Iron 2 plus often will result in like darker compounds, darker minerals, whereas iron 3 plus That's going to be more the reddish oranges that you see in some, like, rust or, reddish minerals out there. So some metals, yeah, it's possible to have more than one charge choice. All right, so we'll cover some of that, and then we'll also do those polyatomic ions as well. All right, hope this helps. Have a good day. Take care.